such that I give pseudo gradient vector field. Is a vector field X on M with two properties. First one, X deriving F is negative. I explain the sign out of the set plus some non-degeneracy condition, which you can write like this: Xf has a non-degenerate maximum at every critical point.
What does XF mean? X dot
XF, I said X deriving F. That means
you apply the
derivative
vector
of
field to the function.
Yes, yes. And I chose to look at descending gradient because I prefer the future to the past, and I look the vector field in the future starting from the point, and I look at where the orbits, the trajectories are going. That is the convention which is used frequently by topologists. So, Tom did such a thing, but strangely enough, Tom missed the transversality condition. It's strange. The founder of the transversality theory. He missed the transversality condition, which is the following. Of course, due to the condition I impose to X, we have for each critical point, we have unstable and stable manifold, because the vector field is automatically hyperbolic, and you have local stable and unstable manifold, and by the flow you have global stable and unstable manifold. And the condition that Tom forgot to specify is the following. It is WP transversal to WSQ for every pair of critical points. This condition has a name today. It's called, one says that the vector field, pseudo-gradient vector field which satisfies this is said to be Morse-Smith. So it was not, this condition was not considered by Tom, and as a consequence, the cells, which there is one cell for each critical point, the dimension of the cell is the index of the critical point, but there are open cells, and the closure of these cells are not controlled. And in particular, the closure of the cells does not satisfy the condition imposed by Whitehead for CW complex. So the cell decomposition of Tom is not the CW complex. So that is the first step of the story. Of course, the next step comes with smell, but I would like to open a short parenthesis, which is this. It is a recollection of an old conversation with Jean-Michel Bismuth, which is this. You can look at take a triangulation of M. Look at the case of dimension 2. So, you have triangles. It is a smooth triangulation in the sense of Whitehead. Smooth. That means each cell is smoothly divided. And you can look at the centers. And there exists easily a Morse function whose critical set is exactly the set of Berry centers. With a minimum index 0 for the vertices, index 1 for the edge, index 2 for the center of the two cells, and so on. And the point is the following. In general, maybe it is well known, but there are a lot of text, even printed books and so on, with this mistake. In general, there is no pseudo-gradient tangent to the triangulation. So it is not possible to have this picture. It's strange. Of course, for the smooth, it is a question of regularity. But I can say the reason why. The fact is the following. Look at a vertex and imagine you have many paths which are coming. And suppose your vector field is like that. it is easy to see that such singularity has no resonance because you must have only one eigenspace for the linearized because you have a lot of vector space. And due to Sternberg's theorem, X is linearizable at P.
So it has a scalar linear part.
Sorry?
It has a linear part proportional to identity.
Yes. But if you have a lot of edges coming, and if your vector field is tangent to these edges, it must be like that, and there is no resonance. And in that case, by Sternberg theorem, it's smoothly linearizable. But in general, a triangulation is not linearizable because it is impossible with one diffeomorphism to make all this line rectilinear. You look only at even by a C2 diffeomorphism, you have not sufficiently many parameters for the two derivatives in order to rectify all the curvature of this. That is the reason why. And it is a standard mistake, and I think that it worth to noticing this.
It was mistake of Graniton?
No. It is a mistake on books you can find in your library. Okay. There is no mistake in Tom. In Tom, there is something missing. In Tom missed the condition of so-called Morse-Mel condition, and in that case, there is no control of the closure of the cells, and it is not a CW complex. In particular, if you take a vertical wheel and you look at this saddle point and the unstable manifold ends at another critical point of index 1, which is forbidden in the case of CW complex, because the closure should be in the zero skeleton. So, what happens with Smale? Smale proves the so-called Poincaré conjecture in high dimension. Is a 1961. It is maybe it is given with more details in the book by John Milner, which is called Lectures on the H-covariance theorem. And it is also detailed by John Franks in a little book whose title is Homology and Phalanx. And I think it is the birth of the Morse complex. And the statement is this theorem. Consider the Morse function x pseudo gradient is assumed to be Morse-made. Then there exists the complex. And then what does it mean? C star fx, which is constructed like that.
Oh, a complex in what sense? In the sense of
I am going to
homology?
explain. I
Or a
explain.
CW complex?
In the algebraic sense. That means the star is for grading, and you have CKFX is a Z module. Freely generated on the set of critical points of index K. F. So it is Z bracket crit K of F. And there is a differential delta from Ck to Ck minus 1, which is given by the following formula. Sorry, I forgot to say that you have to choose an orientation here plus orientation of each unstable manifold. Now, because I forget the rest of the manifold, I only look at I use the letter X for a critical point. You orient this unstable manifold arbitrarily, and now you have a formula for the differential, which is this one. X maps to a sum. X is a generator of Ck, is a critical point of index K of F, and it is mapped to a linear combination with integer coefficient. The sum is over the critical points of index K minus 1. And what is this number? This number is the number, the signed number with sign number of connecting orbits from X to Y. This number is finite due to the transversality condition which is imposed. It is a number of line W of X intersect the unstable manifold of Y. That is a collection of lines. So stable and unstable manifold intersect transversely along these lines. And if you need a number, you can caution by R. You can also count the number. What does it mean with sign? Because this manifold is oriented. This one is co-oriented because the unstable manifold through Y is oriented. So the stable manifold is co-oriented. And when you intersect an oriented manifold, submanifold with a co-oriented submanifold, you get an orientation. And you can compare this orientation with the natural orientation given by the flow. And you get a sign. And it can be proved that this formula is well defined, and D composed with D is 0. So this complex gives rise to some homology, which is now today is called the Morse homology, and it is proved that theorem, the homology of this complex, depending on F and X, is actually isomorphic to the usual homology of M with integer coefficients.
M is X.
Sorry?
M is the same as X.
No, M,
No,
X
M is a manifold.
the gradient.
I see.
M is a manifold.
Yes. Sorry, X
See,
is a
I did not like that because M is fixed,
I see.
but the function, you can change your function. You can change, if you change the function, if you change the pseudo gradient, you change the Morse complex, but you change in the way that the homology is not changing. In fact, you change by so-called quasi-isomorphism. So, the next step is...
Excuse me. I have an equation about the orbits connecting x to y. As these orbits, should this orbit be oriented from x to y or not?
Yes, you have no choice. X is X, it is a pseudo gradient, it is descending. And for a Morse mail, due to the transversality condition, if you start from a point of index k, it is impossible to go by descending flow on to a point of index greater. So there is no choice. You start from a point of index k, and you end at a point of index k minus 1. You can end at a point of index k minus 2, but in that case, you have not a finite number of orbits.
Yes.
In order to get a finite number of connecting orbits, you must have exactly one unit of difference for the units. It is clear? The next step is due to Witten. the famous paper which appeared in Journal of Differential Geometry in 1982, whose title is Super Symmetry and Morse Theory. And it is strange because at some times one says that Witten discovered the Morse complex. It is not true. It is only true for people which are not understanding what Snell has done. But nevertheless, it is absolutely beautiful. And it is the following. I try to explain. It is a deformation of the differential of the RAM seen as an operator on the differential forms. Differential forms. And it is a deformation which is associated with a Morse function. The differential defined by Witten is this. You start by, you take your differential form, you multiply by the exponential of f divided by some constant h. Then you apply the Durham differential. Then again multiplication by a function. So it is, you take the Durham differential and you make a conjugation by such a factor. And of course, because when differentiating here, some constants is at the denominator, you have to multiply by h in front. And you take as h small and going to 0. And what happens? It happens something which is related with the Morse complex. I explain it a little bit. Actually, it was not done in Witten's paper. That paper was a program, and the program was fulfilled by program. By Elfer and Sjöstrand. Two analysts working in France. Appeared in partial differential equation 1985. And I can try to describe what happens. It happens the following. Of course, when you have such a differential operator, you have it a joint. and you can form a Laplacian, written Laplacian, and you can look at the eigenspace of this Laplacian. And the fact is the following. The eigenspace corresponding to eigenvalues sufficiently small
with some
form a finite dimensional complex. That means this what is the
Oh,
problem?
I'm sorry, I didn't understand what you mean by delta Witten. I understand the definition of d Witten, but what is delta?
Delta Witten is formed as usual like the Laplacian by taking d plus a star squared.
Ah, yeah, okay. All right, thank you.
As usual. And the phenomenon is the following. There is a, if you look at, I don't exactly explicitly what is this small, is sufficiently small. But if you look for a given h at small eigenvalues and the small, and the eigenspace corresponding, there are finite dimensional and based on the critical set of F. That is the problem. There is a subcomplex of the complex of differential form, which is finite dimensional. And it is, in some sense, the most complex in this approach. Yes, you have a question. I am not an analyst.
You say that this eigenspaces of Witten Laplacian form a complex isomorphic. The Morse complex,
Yes.
when these eigenvalues are what?
Sufficiently small. Don't ask me what does it mean sufficiently small. But
Okay, does it mean that when you tend this h to be 0, the eigenvalues of delta Witten, some of them become sufficiently small, and some
yes,
of them
yes,
become
yes. So that there is a gap, and the part where small eigenvalues is finite dimensional. That's the point. So now for me it is the end of the story. I explained the role of the approach of Witten. It is very important for what I am to looking at now. So now I look at compact manifold with non-empty boundary. And as I said, the problem is if you try to construct a Morse complex, you need a vector field. And I remember that in the mid of the 80s, I tried a lot, I spent a lot of time for finding such a complex without success, because when you look at a gradient, there are points where the gradient is going out, the manifold points where the gradient is entering, and you can try to combine all, but it is absolutely stable. But from the point of view of analysis, it is completely different, because you can formulate. There is no obstruction for formulation. The problem of looking at the eigenspace of some differential operator. So, actually, it was done by, there is a lot of papers. I mentioned some of them. So, by analysis, it is possible to have a written approach. Of course, you have to put some boundary condition when you look at a problem with differential PV equations. You could put Neumann condition to the boundary, or Dirichlet condition. You have two sorts of problems, but both are solved by different people. At the beginning it was particular case, and then the complete solution was done by the same name I'm giving now.
That boundary condition homogeneous or not?
Homogeneous on, it is a usual boundary condition of Neumann Dirichlet. That means you look at differential forms and you ask, for instance, that they are vanishing in the normal direction or vanishing in the tangential direction. And you get two types of operators with boundary conditions. And the names are the following: Chang and Liu in 1999. And I dropped some of them. Elfer and Nier in 2006, and Colan, what can we read? For correct course, is correct. And Shubin in 2009. Now, Nier is very close to me. He's a mathematician in Brittany, French Brittany, in Rennes, and he called me and asked that I explain more theory to him. And conversely, he explained me a part of Witten's theory. And after this day, I immediately found what is the good vector field which I have to take for defining a complex. So I am going to explain that. Before explaining more details, I have to make a remark. After that, I discovered that some particular case of my problem was solved by Kronecker and Rofka. The book on monopoles and string manifolds, is an impressive piece of work. But it is a very particular case because they look at a situation on boundary manifold, but which can be doubled. But in general, you cannot double a function. Because if you look at what happens on the boundary, you get an angle. And the function is not smooth by doubling. So, in fact, I guess that I am alone to consider the generic case. I explain what I mean by generic case. Manifold with non-empty boundary. That means the Morse function whose critical points lies in the interior of M, and if you define F del as a restriction of F to the boundary, you require that it is a Morse function. Obviously, generic assumption. Now, in that case, you get two types of critical points. So, maybe three types of critical points. Of course, we have crit of F, and the critical points of F del is a union of two types of critical points. I call crit N like Neumann, and crit D like Dirichlet. It is well known. Actually, it was used by the analyst. What is crit N? It is a point X belongs to crit N if the differential of F del at point X is 0. And the differential of F of X, which is non-zero, because by assumption is non-zero, and you calculate it in the direction of the hard-bound, and you ask it is negative. N is a mixture. above the critical point. It is an arch like that.
Shadowed is the complement to the.
No, you are right, you are right. L shadow is L.
Shadowed is M.
It is the outgoing,
Outward.
pointing outwards.
Francois, we usually make a short break after first 45 minutes, so when it will be convenient to you.
Yes, maybe it is 45 minutes now.
Like so, yes. But it is not sharp.
It is not sharp. Okay, I can continue
Yes.
a bit. And I would like to make a break a little bit late.
Okay.
And X is the other type, if the differential is 0, and the opposite sign, that means this picture.
Once again, in the first line, we have a differential of f restricted to the boundary. Yes?
Sorry.
Yes.
I need a break. You are right. And here it is. So, exercise, just for one. For myself, it was my exercise. Try to find x with the following properties. X deriving in f is negative out of f, and x points in 1. Find such a vector, which is descending and pointing in. And of course, it is very easy. There is an obvious obstruction, which is the existence of such points. In such a point, if you look at the tangent space, it is very difficult to point in and to be decreasing. Okay?
And in order to easier understand the pictures, we think about the function f translated as a height, yes?
Of course.
Yes.
Thank you. So, exists, x exists, if and only if the critical point of type Neumann is empty. And after the break, it will be very easy to find what is the good vector field, which computes the homology of the manifold, and which is the vector field, which computes the relative homology of the manifold. Would like to explain that. We make a break for
For 5 minutes.
5 minutes.
5 minutes break.